Okay, today we're going to be moving on to a new section. So this new section is going to be called Virtual Work Principle and Unit Load Deflection Method for Deflections. So before we continue, some brief housekeeping. So I've uploaded the shear videos onto YouTube. Just in case you don't know, when you play the video, you can click there. So apologies to students who already know how to do this. You can click the quality button and you can go into 1080. So you don't need to be watching the video. If you want to watch it in 720, you can watch it in 1080, and perhaps it might be a bit clearer to view. Let me stop that. The other place is on the Dropbox. Sorry, I'm not very good at technology. So if you go to the Dropbox, I've got within here what I call the raw lecture recordings. So if you click the raw lecture recordings, and let's go to the last one, which would be here, you can see that this one is in 3.21 gigabytes. So if you watch it directly off the Dropbox, you may not get that resolution because there may be some compression or something. So if you wanted to watch it in that resolution, just download it and then you can watch it, but that would be in 3.12 gigabytes. So appreciate they're quite large file sizes. So that's the other place to get them. And of course, the third place to get the lecture recordings is the compressed version, which of course would be reduced quality, and they are already available for you on Canvas. So that's where to get the lecture recordings from. What else was there? So if you go onto here, which would be the Harbour Bridge, this, as I said, I'm not very good in technology, but there's a picture of the Harbour Bridge coming up. So that's obviously the repair of the Harbour Bridge, which you can see here. Now you may not be aware, or you might be aware from reading stuff, that they actually use a 3D laser scanner. So they would have used a 3D laser scanner, and we'll probably see later on a scan of the entire bridge. I'm not quite sure why they did that. But they scanned the entire bridge, probably down to very accurate tolerances. Which you can see there. Sorry, that was a guy coming to talk to me about a 3D concrete printer. So you can see the trucks coming along here, and that would be the steel section that had already been scanned and already fabricated in New Zealand, and that's them putting it into place. So you can see all of that from here. Now, so here's a picture of the scan bridge. So that would have been through the 3D laser scanner. And then what you would see down here, more of the scan bridge. And then what you would have seen here is some computer software. So this computer software, it's quite commonly found in the university. We actually have access to almost all software that's available here to do stress analysis. And the reason why I show this is that the compatibility equations and everything within the finite element model have actually been derived. So if you check textbooks, you would see that they would have been derived using the principle of virtual work to ensure compatibility and stuff. So whilst you might not actually feel that you'll be using it in practice, virtual work is, or the equations derived from the virtual work can be seen in almost all the software packages that you would be using as a structural engineer. So let's move on from there. So that's where virtual work may or may not come in. Virtual work is, it's sometimes called the unit load method. So we're going to talk about the principles of virtual work, and then we're going to be talking about the unit load method. But it's something that you just really have to have an awareness of. It's not as if you would be using it in everyday life. And you may have come across virtual work before, say in geotechnics or say in hydraulics. The main application that you may have for doing virtual work hand calculations might be to calculate deflections. So as a method for calculating deflections, which is just one of the many things that it can be used for, it is pretty powerful, and we'll see that later on. Let's have a quick flick through. So again, everything from here comes from Megson, which you can see there. You need to have some background understanding, concepts of free body diagrams, equilibrium, stress and strain, so all of that you've seen before. And then we'll come on to the principle of virtual work, which we'll talk through. So there's a bit of mathematics, which is not really too bad when you understand how to apply it. So work is really just force times distance. So I'll talk about signs in a second. You can see some work some in-class examples here. Find the reactions using the principle of virtual work. We move on to virtual work of a deformable body. We'll talk about the virtual work of internal forces, and then we would come to equation 18, which I'll be explaining how you can use to apply equation 18 to work out deflections. So deflections of trusses. Now when we have beams or cantilevers, which isn't a truss, so we can see the notation here. N stands for the axial force, and EA is the Young's modulus and second moment of area. When we come to a beam and bending, you might like to have a look at this equation here, equation 22. Okay. So say for example I wanted to calculate the deflection of a cantilever at its tip, I might be using equation 22. So let's flick on through the notes, and then after that we will get onto the signs of external and virtual work. And then here's another equation which is important, of course, that says that external virtual work and internal virtual work need to be the same. So that's a so you would equate external virtual work with internal virtual work. After that, we'll be talking about well, the unit load method, how to graphically integrate, because we will be, for example, needing to, if you've got a cantilever and you've got another beam here, don't worry about this, I'll go through it in a second, but if you draw the bending moment diagram of that one there under a load P, and then here you had a virtual load, which I'll put a dash on top, you might want to be integrating these two functions when you multiply them together. So you may or may not have observed that when we flick through, and when we look at equation 22, you may or may not have noticed that that's an integral of two bending moment diagrams divided by EI. So there'll be fast ways to do the integration. You can do it manually, just work out some functions, multiply the two together, and then use that. Or there are some techniques which would speed up your usage or the ability to integrate functions. And so after that, we come to this next example here, which is compute using graphical integration. Okay. And then after that, an example, which in this case here, that would be a cantilever truss system, and it's asking us to calculate the vertical direction, the vertical deflection at that point, using the theorem of virtual work. So virtual work can be applied to trusses to work out deflections, and it can be applied to cantilevers to work out deflections, as I've said just now. Now, before we go on, so I'll return back to the Dropbox. Just give me a second while I find it. So we go there, and so if you look under virtual work, and if you look under the in-class questions, and then that would be the first one, second one, and say the third one. So let's go to the third one. We have got video solutions. So there's a video created by one of the TAs that goes through the solution of that in the form of a movie file, which you can play and go through everything in detail. So that's available for you on the Dropbox if you want it. If you don't want it and you just want to see the solution and you don't want to have to commit to wasting your time having to listen to someone like me talk for a long time, John Butterworth he typed out some solutions, which I call the John Butterworth solution, and you can just look at the solution and maybe that would be enough and you don't need to spend your time looking at the videos. But there are videos that have been uploaded onto Dropbox in those locations that I've just shown you. So don't get too bogged down with the mathematics at this stage. It's not particularly terrifying, and it's more a case of application like most things. So I thought that we could have a quick look at the 2019 exam paper. So we've got the slope deflection method question, some qualitative question, you've got a shear question, and then a buckling question, and then this one here would be the virtual work question. So this question here would be virtual work, and this one here would be the flexibility method, which requires you to use virtual work in order to work out your deflections. So the flexibility method, which would be the next section after this, would need virtual work in order to be able to do that question. Okay. Right, so now let's have a look at the appendices of the course. So this is what you will get in the exam. So you may or may not recognize that. That basically says the external virtual work is going to be equal to the internal virtual work. This would say, what is your deflection? So that example 3, or the cantilever. So you've got a cantilever under a load P, and that cantilever would deflect something like that. For this case here, we would be calculating two bending moment diagrams and multiplying them together and dividing by EI, and that would give you your deflection. So you would be equating external virtual work with internal virtual work. And in the particular case of a truss, so if you've got a truss system like that, so that's not a beam, but it's a truss, and maybe you had a load there, for example, you could use virtual work, or this equation here, work out the axial forces in each of these members, work out the axial force in another compatible situation, and then use this to be able to work out what your deflection is. Now, in terms of the integrations, you probably, or you may be seeing this in geotechnics at some stage here, and this is just a quick way to integrate, and sorry, it's a quick way to calculate centroids of shapes. So if you had a straight line passing through that, n equals 1, so linear function would be that, quadratic function may be that, and then a cubic function may be that, and then this equation here tells you where the centroid of the section is, so where the centroid of the parabola is, or the centroid of the quadratic function. So we'll talk about this one later on, but this can be used in the so-called graphical method for calculating, for multiplying two bending moment functions together, for example. And then it would be used with this. So with that method, if you've got a straight line, that's one function, and then you've got a cubic or something else as another function, this is a quick way to work out the integration. Probably a faster way to do the integration, however, is this appendix here, and this appendix will be given to you in the exam, of course. So don't get too worried about the first time you see it. Like most things, it can be a bit scary, but it's not actually that difficult to apply. Probably the one that's important, or the one that's the most general, is this one here. So equation 2(3) is L over 6 to A2A3 plus B2B3 plus A2B3 plus A3B2. So when you've got two linear functions and you wanted to integrate them, that is probably the equation that you should be using. As you develop more confidence, you might be able to find other equations which can get you there a bit faster. Okay. So nothing to worry about too much. We'll talk very gently about how to use these equations. So before starting on, I thought it might be better just to give you an example. So we'll go back to this section here. So I've got something which I call rigid. So it's a bit of stone actually. So you could call it a rigid particle or something. Now, if this is my rigid particle, and if I applied a force to move it in that direction there, the work done, so work done would be equal to the force that has been applied multiplied by the distance moved. So I think everyone should be quite happy with that. You've got your particle here. I've applied a force F to my particle. My particle has now moved to a new position. So it's moved by a distance delta. It's moved by a distance delta from there to there. And the work done is going to be the force times delta. So if I've got the same particle here, so same particle here, and now I apply a force in that direction. Okay, you apply a force in that direction, and then it makes a displacement in that direction there. So that direction is made a displacement delta, and you can see it's moved a distance delta, and you would say the work done is equal to force times delta. So you can see when I move my particle from here to, when I move my particle from here to here, the delta, direction of movement, and the force were in the same direction. And so we say that the work done is positive. Okay, so the work done here is positive. Now here I've got my particle, and I've applied a force to my particle, and then it's moved a distance delta. I would also say that the work done is positive. So as long as the direction of movement delta is in the same direction as the force, you would say that positive work has been done. So I hope everyone's okay with that. Where you may get some problems is where you apply, so I've got, if hypothetically, I'm starting off here with a force, and let's say you start off with a force and it's acting in this direction, but your particle moves in the opposite direction. So let's say you've got a particle here, and then it's moved here by a distance delta. So you apply a force and it moves in the opposite direction, then the work done in this case here is negative F times delta. Okay. So as long as your particle moves in the same direction as the force, then positive work has been done. But if your particle moves in the opposite direction to the force, then negative work has been done. So that's just laying out the guidelines. So if it's in force is in the same direction, positive work has been done. If the force and the direction of movement are in the opposite directions, then negative work has been done. And we've introduced the concept of work done is equal to force times distance. Right, so hope everything's okay with that for now. Now, let's have a look at how the theorem of virtual work is applied, and then after we've shown how it's been applied, then we'll go through the theory in the course book, and maybe that will make a bit more sense. So right here, so remember that this is actually example 3 in the Dropbox, and remember there is a video solution by Zoe who goes through all of the calculation steps, and I have a LiveScribe solution anyway, which I've stuck on YouTube, going through the same thing. So of course, when you do these sort of problems, you need to use method of sections and method of joints to work out the forces acting in each member, and I won't go through that at this moment in time, but they will be gone through if you watch this video here or if you watch that video there. So either 1 or 4 will be covering it. Okay, so let's continue, and here I just want to show you how to apply the theorem of virtual work to work out some deflections. Okay. So this is the layout of a truss. So this is the layout of a truss here. Give me a second. Sorry about that. So here's the layout of a truss, and right here I've just given the lengths. So we can see that it's a truss. The first bit of the truss has a length of 4 meters. The second bit, the second horizontal bit of the truss has a length of 8 meters. Up here there's 8 meters up there, and then you connect your 2 vertical members down here, and then back down here of a length of 5 meters. So that's your truss here. Now we're saying that the Young's modulus of the Young's modulus is 200 times 10 to the 5 kilopascals. So that's just the stiffness of the material that's been used for the truss. And then right here we have the cross-sectional area of the truss, which is A. Okay, so what are the steps? Now let's say that our truss is under a vertical load of 90 and another vertical load of 90. So we've got a truss here, and I've applied 90 kilonewtons here, and I've applied 90 kilonewtons here. And I would like to know what my deflection at the end of the truss is. So the question is, it's under 90 kilonewtons and 90 kilonewtons. What is the deflection? What is the vertical deflection of the truss at the end here? So what you would do is you would do method of sections, method of joints. So you would take equilibrium of that point, and you would find that there's this member here is in tension, and you would find that this member here is in compression. You would find, using method of sections, method of joints, that this member here is in compression by 480, and you would see that these are in tension by 300, 150, and 240 respectively. So method of sections, method of joints, something that you would have covered in your first year, that would be used to calculate the axial forces in each of the members. And if you're not sure how to do that, as I said, don't worry, you can go back and watch the video tutorial, which will go through all of the steps. Now, let's now say that we've got another truss. Okay, so it's the same truss, but it's got a different load on it. Now the load, so we can see that the load we've applied here is what's termed a virtual load, and you can see that it's got one hat, which you can see there. So hat, this hat, or this line that's drawn over it, is how the course book would show a virtual force. Okay. Now, the virtual force can be anything. So sometimes students do get confused and just think the virtual force could be anything. It could be the mass of Peppa Pig multiplied by gravity, so it can be anything. It doesn't have to be 1 kilonewton. Okay, it doesn't have to be 1 bar kilonewton. It can be anything. So the virtual force is applied at the end. And why is the virtual force applied at the end? The virtual force is applied at the end because that is where you want to work out your deflection. So wherever you want to apply the deflection, wherever you want to calculate the deflection, that is the point at which you apply the force. Okay, so we want to know this deflection there. So again, method of sections, method of joints. You can use method of sections, method of joints, and you would be able to calculate the forces in this member here, and sorry, in this structure here. And you will see, again, I've indicated which ones are in tension, which ones are in compression. So you can see the C there is in compression, and the rest is going to be in tension. So I've got a small model anyway, so I'm not sure if this can be seen under the camera. So let me try turning this around. No. Okay, so I'm going to have to zoom out. Right. Okay, so I've got a small model anyway, which you can see here, which doesn't quite fit under the camera, unfortunately. But let's apply the load there, and hopefully you can see, well, we can see which members are in compression, obviously. So these members are in compression, just because they've got some desire to buckle. Okay. But method of sections, method of joints will tell you the forces acting in each of the forces acting in each of the members. So what do we do now? We evoke an equation, and the equation that I like to write out is external virtual work is equal to internal virtual work. So external virtual work is equal to internal virtual work. Now, if we go back to the course book, equations 9 and 18, which I showed you before. So equations 9 and 18. So equation 18 is there, and equation 9 is there. And equation 9 would be saying that would be the external virtual work, which is the sum of the forces against the virtual displacements. And equation 18, particularly for a truss system, is shown there. So the notation that we use is W for work, V external is equal to W of V internal. So when I was in undergrad, I guess I was using EVW and IVW, but that's the notation. So external virtual work is equal to internal virtual work. So the external virtual work is going to be equal to the virtual force, or the imaginary, sometimes called dummy, sometimes that. So whatever force you've applied to the system, multiplied by the deflection. So we want to know, this is the deflection that we want to calculate. So as I said, that can be anything. It can be, so that doesn't need to be 1. It can be anything. It can be anything at all. And you would probably see that if that was 2 and not 1, then all of these forces would double anyway. So it can be anything because it's all going to cancel each other out in the wash. So external virtual work's very easy. It's just the external, it's just this one bar that you've applied to the system, multiplied by the distance that the real system has moved. Now, because these are this is a truss system here, which you can see, the internal virtual work for each of these is going to be, let's start with this member here. It's going to be the length of the member multiplied by the force in the member of the real system. So this one is termed the real system because that's the real forces that that's the real system that you're trying to solve. So 240 would be coming from the real system, and then this 2.67 obtained from methods of sections, method of joints for a 1 bar kilonewton, multiply that. So it'd be that value multiplied by that value multiplied by that value, which you can see there. That is for the first member. And then we've got the next member there. So this member here is of length 5. It's got 150 acting in it, and it's got 11.67 acting on it, 11.67 bar in the virtual system. Then this member here, 300 times 1.67 times 5 plus 150 for this one here times 4 bar times 5 plus 480 times 4 times the length, which is 4, plus the final one is 120. 120 multiplied by 1.33 bar multiplied by 8. And you divide all of that by EA, which you can see there. So all of it, everything's been divided by E multiplied by A. And if you work all that out, it cancels out anyway because the bars on both sides. So the 1 bar cancels out anyway. And what you will get is the real deflection of 0.119 meters. So in a nutshell, that just shows you how to apply virtual work in order to calculate deflections. And we will go through the proof later on, but it's not really necessary to know the proof. It's more necessary for the purposes of passing the exam to know how to apply it. Okay, so that's one example. for the truss system. Now let's do another one. So this time here, move that to one side. I'm going to say that I've got a cantilever, and I've got a load acting on the end of the cantilever, and that's going to be P. So I've got a cantilever acting on the P, and this time here I'm going to be saying there's going to be a second moment of inertia of the cantilever about the major axis. I'm just going to leave that in terms of algebraic notation, and there's going to be an EI. So E would of course be the Young's modulus. So the bending stiffness of this member here is going to be E multiplied by I. So let's keep it real. So this is the real system. So the real system would have a deflection like there, and it would be like that. So the originally you've got this load P, and it's going to have moved by a distance delta. Okay, and we want to calculate what delta is. So we've now got the virtual system, and I said with the virtual system you can stick anything on it. So we've got our load here, and then we would stick, I'll just show it in dotted lines, this 1 bar. So I'll be sticking 1 bar on top, which can be anything. And now we want to know how we can calculate the deflections. So the deflection delta. So again, we come up with theorem of virtual work, or the unit load method, and we would say external virtual work is going to be equal to the internal virtual work. Okay, so that would be the first equation that you write, and then we would set that up in the notation as our W V ext. For the external virtual work, being consistent with the course book, is equal to W virtual work int. So don't worry about the proof. We'll prove why this works later on. So the external virtual work is of course going to be equal to this 1 bar multiplied by delta. So the work done is going to be the 1 bar times the delta. So we'll put the 1 bar, and then we'll put the delta, okay, where the delta is to be calculated. So that is the, here is the virtual system on which, or the virtual set of equilibrium on which the real system is applied. That's like one way to think about it. Now in terms of the internal virtual work, let's skip along here to equation 22, which you can see here. And we can see here that the internal virtual work is going to be equal to the bending moment diagram of the virtual multiplied by the bending moment diagram of the real divided by EI. So we'll go back to the... So let's plot a bending moment diagram. So we can plot the real bending moment diagram, which would look something like that. Okay. And then we'll say that's the length of the system here. So I'm trying to derive an equation, basically. So the bending moment here at the end is going to be PL, since P times the distance there. And under the 1 bar, it's going to be, the shape of the bending moment diagram is going to be the same for the virtual. So that's the real and that's the virtual. And the shape of the magnitude of the bending moment is going to be 1 bar multiplied by L, of course. So in order to work out my deflection, I need to integrate the real bending moment, which we'll draw there, and I need to multiply that by the virtual bending moment diagram, which would look like there. Okay, and then I need to, let me check, so divide, I think I'll keep that outside, so I'll put 1 over EI here, to keep the EI, since the EI is constant for that, and it needs to be 2dx, of course. And the units, the integral would go from 0 to L. Okay, so we need to be able to work this out. So later on we'll get more complicated stuff. But if you've got two functions of two straight lines there, we can flick back to the appendices booklet that you will be given in the exam, and we will have a look at trying to use the one that I identified, 2, 3. So let's have a look at 2. So A2, so let's just line it up here. As long as the functions are linear, this one always works. So instead of sticking something on Piazza saying you don't understand why you can't use other ones, just try 2, 3 first. So A2, in terms of this end here, so A2 for this one here, so that one there has 2, so A2 is going to be equal to PL, okay, and B2 is going to be equal to 0. Okay, so that that line can be constant, it can be inclining, declining, whichever way you want. We just have to work out the numbers, and then so that takes care of 2. And then for the 3, which is that shape there, which is the same as that one there, but because we've got a different function, even though it takes a similar shape, which we'll see there. So this one here, we would say that A3, which would be the peak value there, A3 is going to be equal to 1 bar times L, okay? And again, B3 is going to be equal to 0. Okay, so we've got that equation there, which we need to integrate, and you're more than welcome to work out that equation there and that equation there, and just multiply the two equations together and integrate, but you'll probably come up with the same thing, and I'm just showing you how to do this quickly. So 1 bar times delta is equal to, go back here, we can see the equation for 2, 3. The length of the member is L, so it's just going to be L over 6, since we've set the length there. 2 times A2 times B3, so A2 times B3 is 0. B2 times B3 is going to be 0 times 0, is going to be, so that's 0 as well. A2 and B3 is 0, so that A2 multiplied by B3 is 0, and and A3 times B2, so A3, which would be that one there, times B2, that one is going to be 0. So sorry if I made a mistake when I was reading this out. I actually have a bit of trouble seeing. So we have A2 multiplied by A3, and A2 is PL, and A3 is 1 bar L. So let's substitute that into the equation. So we multiply that by A2 times A3, and that's going to be equal to PL, which is going to be your A2, and multiply that by A3, and that's going to be 1 bar L. So 1 bar L. So remember that I just keep on reinforcing that 1 bar can be anything. So it can be that in the virtual world, it can be anything, because it's whatever it is, it's just going to be removed in the wash. And so you would then say that your delta, which you're trying to calculate, is equal to L over 6. Sorry, I missed a 2 there. So sorry, I missed a 2. So it's L over 6, 2 times that. So I missed out the 2. So it's going to be 1 over 3, because 2 and 3 becomes 2 and 6 become 3, and P times L sorry about this, it's going to be L over 6 . So that's going to be 1 over 3 times, put that P, and then put that as L cubed. So the delta is going to be PL cubed over 3. So that's the application of the theorem of virtual work in order to calculate deflections. So let's move back to the truss example, which we see here. So we'll move back to the truss example. Sorry. Which we'll see there. Now, at the start, we were talking about the sign convention. So we were saying right at the start that if the force is acting in the same direction as the deflection, then that's positive work. So we can see in this example, going back to the first one here, that this force and this one here, they're both the same. So positive, so that number then becomes positive. So we can see that this one and this one here, they're both the same in that they're both in tension, and so that's positive. We can see this one, which is in compression, and that one here, they're both in the same direction, so it's positive, and so on. So when we're doing this virtual work calculation, just think about, just remember that if the two things, if the real and the virtual, if the forces are in the same, i.e. tension and compression, then it's going to be positive, which is why everything here that you can see there has got a positive sign. And then we divide by EA, and then you get your deflection. Now, in this example here, for this deflection there, we can see that the bending moment is on the same side. So because the bending moment is hogging, so we've got hogging multiplied by hogging, and that's the same, it's positive. If it was sagging multiplied by sagging, then it's the same and it is also positive. But when you've got hogging multiplied by sagging, then whatever you do for the integral will turn out to be negative. So I just mentioned that at this stage here, just to sort of explain where the sign convention is going to be coming into it. So this is the application of the virtual work method, and what we'll do now is that we'll have a look through the course book, and we'll try to explain where these equations have come from. So I'll take that one out there. So this part lays down the ground for statically indeterminate structures. So we'll be talking about the flexibility method next, and the flexibility method in the next section requires deflections to be calculated. Deflections is what we've just shown, for which reactions, internal forces cannot be determined. So we already know how to solve statically indeterminate structures. That can be calculated using the slope deflection method, although that's just the deflection due to bending. I'll explain deflection due to shear a bit later on. But that's the point of this bit, to lay down the groundwork to show how deflections can be calculated. So methods of analysis that use concepts of work and energy, and in particular principal virtual work, has many useful extensions, derivations, applications, and as I mentioned, the analysis of the bridge that I just showed, that would have been analysed using what's known as the finite element method, and the theorem of virtual work would have been used to derive the underlying theory to that. So we come across what's known as the unit load method, and sometimes students get a bit confused when they first see it because they get a bit confused about that one bar. So as I tried to say in the example, it can be anything, okay? It can be any load. The unit load method is used as a basic tool for the so-called flexibility or force method, which we'll see in the next chapter. So this is the principle of virtual work. The work done by forces and moments. So work done is equal to force times distance. So here I've got a particle, and then it's moved a distance, and the work done is just the force times distance. So notice that there are vectors, and their work is a scalar product. And if you went from there to there under that force there, then of course you're going to have to take the product to work out the component of the force that acts in that direction, delta, before you calculate the work. For distributed loads, you can do something similar. So that's just an integral for the distributed load over force times distance, where that is the deflection of the beam. Now, there's also one for moments. So the work done by a moment, you can see here they're just broken up into two forces, but the work, or a couple, but the work done by a moment is the moment multiplied by the rotation. So moment multiplied by rotation is the work done. So we now come on to the principle of virtual work for a particle. So let's suppose that we've got our cantilever like this, and then I'm applying a deflection there. There are lots and lots of particles within this, so this cantilever is made up by a lot of particles, and under the force that I've applied there, or the force of displacement that I've applied there to get to this state, every particle within here is in equilibrium. Okay, so each of the millions and millions and millions, probably billions of particles, if you grab each one of them separately, you say a particle there, you would be able to, if you so wished, to work out the forces acting on that particle. So this is a particle in equilibrium. Okay, so the particle is in equilibrium. Now, what happens when you got your particle, the particle is under some forces which make it in equilibrium? What happens when you move it by a displacement u, by a displacement u bar? Can you calculate the work done by it? So since the particle is in equilibrium, so let's try and give a simpler example. So suppose I have a particle maybe in my truss system. So I've got a particle within here, and let's say we're interested in the particle there. The particle is under compression. So we've got a particle there, or at the top face is under tension. So that particle is in equilibrium by these two forces. So I'll just call these forces F. Okay. So the particle is in equilibrium, and in effect the net force on the particle has to be 0. If it wasn't 0, then you're using force equals mass times acceleration, and your particle is accelerating off somewhere. So the particle has to be in equilibrium. So if you move your particle from here to any point or any virtual point, so I come along and I move my particle from here to here, and I still, what is the work done by the force, by these forces? Yes, I can work going from here to here, for example. Yes, I can work out the force done by this one, work equals force times distance. Yes, I can work out the work done by this force, which would just be force times distance. The distance moved obviously in that angle. But because these two are equal and opposite, overall no work is going to be done. So we can say if a particle is in equilibrium under the action of concurrent forces, then the virtual work done by the forces during any virtual or imaginary displacement is 0. So wherever I move the particle, because it's already under equilibrium, if I move it there, for example, and still keep the same forces, so I'm not changing the forces, I move it from here to here, the work done by the forces is going to be 0. So I hope that's all clear. So the virtual work in this case is, the virtual work is of all of the forces, the sum of the displacement, and then you're working out this force here in that direction of the displacement, which would be the cosine of the force, and that's going to be equal to 0. So we can now state a virtual force variant of the principle of virtual work if a particle is in equilibrium under the action of concurrent virtual forces. Then the virtual work done by the forces during any real displacement is 0. So by concurrent, it just means consistent with the system. So what's the principle of virtual work for a rigid body? So a rigid, i.e. non-deformable or infinitely stiff body, which might be something like that, can be understood as a collection of particles that do not move relative to one another. By applying the principle to the individual particles, just give me a second, sorry. By applying the principle to the individual particles of the rigid body using virtual displacement, principle of virtual work can be generalized to a rigid body. So if we had, for example, a beam, okay, so we draw the beam like that, and we say that this beam is rigid, so we'll be saying EI is equal to infinity, because that would be rigid, so a really, really stiff beam. And if we had a load acting on the system there, okay, so we put a load there, and so we put a load halfway across, and then we say that's 1, okay, so 1 kilonewton or whatever you want it to be. And your beam itself is rigid, which means that it's not elastic, which means that the beam itself doesn't deform. So the beam is not an elastic body that can deform. So can we use this theorem of virtual work that we've just stated to work out what the reactions are? So there would be a reaction RA and there would be a reaction RB. Okay. So of course you can take moments about a point to work out RA and RB, but let's try and use virtual work to see what the forces would turn out to be if we use this theorem. So a rigid body, that's your rigid body. It's in equilibrium under the action of a concurrent force. So this rigid body is in equilibrium under RA, RB, and the 1, and it's not moving, of course, because it's in equilibrium. Then the virtual work done by the forces during any compatible virtual displacement is 0. So let's suppose that I come along and I just move my beam, this rigid body. So I've not violated anything, I've just rotated it. So it's still under this 1, okay, so it's still under this 1 kilonewton or whatever. That's RA, and then that's RB there. And I've just come along and I've just moved it. And I've moved it by, let's just call it a distance delta. Okay, so I've come along and I've moved it by a distance delta. Let's use the principle of virtual work for a rigid body to work out the reactions. So if a rigid body is in equilibrium under the action of concurrent virtual forces or real forces, then the virtual work done by the forces during any real displacement is 0. So all this is saying is that just make sure that equilibrium is satisfied. So the virtual work done by the sum of all the particles, of course, has to be equal to 0, as we've just shown. So this bit here, this force here, that's moved by a distance 0.5. So it's moved by a distance 0.5 delta. So if that's moved by delta, that's moved by 0.5 delta. Now we've got the force, this force here. So this force doesn't move, so it's done no work. So this one has done no work. This one has done 0.5, but that one is going in the opposite direction. So we're going to say that this has done negative work. So this has done negative 0.5 delta multiplied by 1 in terms of work. Now, what work has this force done? This force here on this side has moved by a distance delta, so it's done some work, and the work done is RB times delta. So we've got RB times delta there. And what we're saying is that the sum of all the work done has to be equal to 0. So let's say, let's move that to the other side. So RB delta is equal to 0.5 delta, and then we cancel the delta, and then we get RB is equal to 0.5. So by using the theorem of virtual work for a rigid body, we've been able to calculate that RB is 0.5. Okay. And you can do exactly the same thing, and you can work out what RA is. So in the tutorial that in the video tutorial Puya probably covers this case as well, under a UDL. Where that EI is equal to infinity, and using the principle of virtual work for a rigid body, he's probably able to show what these reactions are. So that's just another way of doing it instead of using equilibrium. Okay, so let's move on. Now we come to the principle of virtual work for a deformable body. So here's a rubber, which is obviously not the same as something like that. So if the body in question is deformable, when the virtual displacements are imposed, they will also cause internal deformations. Okay? So if we went back to the example that we just showed, when you've got your cantilever, the cantilever is an elastic, it's not a rigid body, it's an elastic body, so there will be some internal deformations. Okay, otherwise it wouldn't deflect. So one might imagine the cantilever is made up of many particles inside it, and mutual contact or internal forces between the molecules or particles will perform work on the internal deformations. So the virtual displacement principle is very similar, but internal virtual work is no longer zero, and so must be included. So if we have a deformable body in a state of equilibrium, so here we've got a deformable body in the state of equilibrium, and it's now given a virtual displacement compatible with the constraints and boundary conditions, the total work done will be zero. So we've got a deformable body there, and if it's now given a virtual displacement, so if we now displace all of these particles, and that's compatible with the constraints, so a displacement compatible with the restraints would be of that order. Okay, the total virtual work is zero. So I think that should make sense. So the principle of virtual forces is if a deformable body in a state of compatible deformations satisfying the boundary conditions and internal constraints is acted on by a system of virtual forces which are in equilibrium, then the total virtual work done by the virtual forces acting through the real displacements is zero. So as long as our two systems are compatible, so here these two systems are of course compatible because they all obey the constraints here, then the total virtual work done is zero. So this latter form of the principle is useful for determining displacements corresponding to known forces, and it is the one that will be used for the unit load method, which we've already introduced. A deformable body changes shape under applied loads and may be subjected to virtual displacements that not only change its position as a whole, but also deform it. Under such virtual displacements, both the external and the internal forces do virtual work. And that's why later on we're saying, for this case here, that the external virtual work is going to be equal to the internal virtual work. So let's work out the external virtual work. So we've got point loads P, we've got UDLs, there's moments that you can apply. and it's generally straightforward to calculate the external virtual work by summing the components, by summing the separate components together, which is just in the case of P times displacements, the integral here of the UDL multiplied by the displacement of the beam and the moment multiplied by the rotation, or virtual loads times their corresponding real displacements. So you can see that the virtual one is shown with a dash, is shown with a bar up here, and what we're saying is that you can think of it either way around, either real against virtual or virtual multiplied by real. And if you do that and you work out the external virtual work done, then you would find that that is equal to the internal virtual work. So that deals with the external virtual work. Let's now deal with the internal virtual work. So we consider a tiny element within the structure. dV, or the volume, is dA times dL. So this is why in the truss, which we saw here, so the work done is equal to the axial force times the virtual displacement over the entire length, or the entire volume. That's why we were multiplying by the volume before. So here is the the volume is the area multiplied by the length. So those truss members, the area multiplied by the length, and then you've got either a real stress or a virtual strain. So we've got our two scenarios, and both of which are compatible with each other. So in the case of here, we've got the real case, which is here, and the virtual or the imaginary case, where the imaginary case is consistent with the boundary conditions. And if you multiply the real stress multiplied by the virtual stress, and you did the integral over the volume, you're going to be able to get the virtual work internal. So the virtual work internal is virtual stress multiplied by real strain over the volume dV, and that will give you the internal virtual work. So that deals with direct stresses, and we've got exactly the same arrangement when it comes to shear. So you can see the virtual work internal, due to the real shear stress multiplied by a virtual strain over dV, would give you that equation there, or expressed in this way here. So what you can see here is that we can interchange quite easily whether it's the real stress or the virtual stress. Okay. So it's either going to be real stress multiplied by virtual strain, or virtual stress multiplied by real strain. So you can think of these two as being completely interchangeable in terms of working out the virtual work. So that takes care of the direct stresses. That takes care of the shear, which we can see there. And here, with the axial force, we've got the real stress. So these would be, in this case here, this would be the real stress, force divided by area. And on top of that is you're subjecting that to the strain from here, and the strain from there is going to be equal to the virtual force divided by Young's modulus divided by A, and then the internal virtual work for that becomes that. Okay, so that was what we did. That was what we did there. Now the final one is the bending moment, which is when you've got bending. So here these are the direct stresses, and of course bending is, there's a variation of direct stresses when it's under a bending moment. So consider a structural member of length L subjected to a real bending moment. So the real stress is sigma equals my over I. You've applied a compatible virtual strain, and there's a relationship between the virtual strain and the rotation. And then back from the engineering theory of bending, we've got the virtual rotation is equal to the virtual moment times L over EI, and then the internal virtual work becomes that equation. And that was what we did here to calculate the internal virtual work. Where it is again emphasized that the real and the virtual bending moments as well as the section properties may change along the length. And then if you use the virtual force variant of the principle, we could end up with exactly the same results. So I've explained the process. Apply the virtual force at the position where you are trying to work out the deflection, but these are completely interchangeable. So once we're calling this real and we're calling this virtual, in terms of the maths, it could be the other way around, and you would get exactly the same answer. So for the shear force, we would get a very similar equation. The real multiplied by the displacements divided by GA, and that would be your virtual internal work. And then you can apply the same to a torque. And if you wanted to work in 3D, then you've got bending about 2 different axes. Okay? So you can consider all of these in your equation. So this then becomes the general equation for a space frame, but for our purposes, we've used the axial force bit for the truss example, and we've used the bending moment bit for the cantilever example. And this bit here just says what I said at the start about the force and the displacement needing to act in the same direction. If they do, then you get something that's positive, and if you don't, then you get something that's negative. So we can show that later on in the examples, but that's basically why compression multiplied by compression here worked out to be positive. And of course, that gives us the relationship between the external virtual work and the internal virtual work. External virtual work equals internal virtual work in that example here, and external virtual work equals internal virtual work there when we were calculating the deflection of a cantilever. So I think that's where we'll stop today, and tomorrow we'll talk about the unit load method or the dummy load method, but we've already shown the application of that. That was the unit load with the bar sign, and that was the unit load here with the bar sign here. So the general case is wherever you want your deflection to be calculated, just apply a unit load in that direction and then apply the virtual work equations as we've just shown. So we'll do this tomorrow, and after that we'll come up with some of the faster ways to do the integration.